We are from Vin AI in Vietnam. Today, we present our work toward realistic single-view 3D object reconstruction with unsupervised learning from multiple images. In this work, we propose a method to solve the 3D reconstruction problem from a single image. Our system learns from a multiple image dataset in an unsupervised manner and produces realistic results. And what is our motivation? Our problem is recovering the 3D structure of an object of a known category from a single image. It is a challenging task due to its ill-posed nature. However, humans are very good at this by knowing the 3D shape prior, which has been learned every day since birth. So, how to let the computer learn the 3D shape prior? The first approach is supervised learning. This approach has a huge drawback. It requires massive 3D data, which is hard and expensive to acquire. The second approach is unsupervised learning. It does not require 3D ground truth data, but learns the 3D prior via observing 2D images of the same category. This approach has successfully been demonstrated by a recent work of Wu et al. To make the unsupervised training converge, this work targets modeling symmetric objects and effectively exploits the symmetry constraint. We call it LESSM, which stands for learning from symmetry. However, the symmetry constraint limits the application of this work and makes it fail to recover asymmetric details. Instead, we look for a more general solution. We observe that many datasets provide multiple images for each object instance, such as multi-view dataset, image collection with multiple images per object, or video sets. We call them multi-image datasets. Note that a single-view image set of symmetric objects, like in LESSM, can be considered a multi-image dataset by adding the flipped images. We can exploit these multi-image datasets for our unsupervised network training. The 3D shape of each object instance is consistent across its images, providing a strong cue for 3D reconstruction learning. Based on that idea, we developed a novel framework called LEML, which stands for Learning from Multi-Image Datasets. LEML learns the 3D prior from multi-image datasets such as multi-view, image collection, or video in an unsupervised manner. At inference time, it only needs a single image input to recover the object's 3D structure. And here is the system of LEML. LEML feeds the input images of the same object into a decomposing network to extract the view, light, canonical albedo, and canonical depth of each image. These components can be passed to a differentiable renderer to recover the input image. LEML compares the reconstructed images and input ones in a reconstruction loss. But that is not enough for model convergence. We also employ cross-view rendering to exploit the availability of multiple images per object instance. Each input image is reconstructed using its own extracted view and light, but albedo and depth map of another one. This reconstructed image will be compared with the corresponding input image to form a cross-view consistency loss. For sharper 3D reconstruction, we use an albedo loss to regularize the albedo map to avoid texture overfitting. This regularization guarantees that the albedo is smooth at non-edge pixels while preserving edges. An albedo loss requires 3 aligned inputs, including an input image and the corresponding maps for albedo and depth. The weighting terms suppress the effect of neighbor pixels that likely come from other regions due to a large gap in intensity and depth compared with the current one. It enforces smoothness on the albedo map. And here are the results of LEML. We test LEML on various types of datasets. First, it covers the datasets with single images of symmetric objects, similar to LESSM. Then, it excels on other dataset types, including multi-view, image collection, and video sets. As you can see, LEML achieves better results compared with LESSM. It particularly outperforms LESSM on the multi-view and image collection dataset. Let's take a look at some animated shapes in these datasets. First, LEML performs well on a single image dataset of cat faces. It performs extremely well on multi-view dataset like multi-pi. It still well converges on the Kasia dataset, an image collection set of vastly diverse images. And that model can produce realistic 3D models on in the wild images, even on drawing. Quantitative results on the BFM dataset show that, compared with LESSM, it achieves a better mean angle deviation number with 1 degree decrease, implying better reconstructed 3D surfaces with details recovered. LEML also dominates the baseline method in user surveys on 3D reconstruction quality in every dataset. Thank you for listening.